Hello everyone, this is Peter from Pythonista with one more video. Today I'm gonna talk about Delta Lake logs. I got inspiration about this talk in the book that I've read beginning of this year, maybe 2 months ago. It's called Delta Lake: The Definite Guide, the Definitive Guide. So it's a book written by the engineers that created and maintained the Delta Lake. They are mostly Databricks employees that maintains this library, which is open source. This video is not an introduction or an explanation of what Data Table is, but it is a deep dive of understanding the logs, which is at the heart of what a Delta Table is. So the introduction of Delta Lake or Delta Tables is to solve a problem that they had in the data lake, which is to have a transactional log to offer ACID compliance, ACID, that I've talked about in the other video. I'll put the link in the description, but basically is atomicity, consistency, isolation, and durability. So if you wanted to have a copy of this book, you can scan this QR code or access the tiny URL, and then you can download this book for free. Or if you like to buy it, it's available in Amazon for about $50-$60. I bought in Australia. So, but the Databricks make it complimentary. So let's deep dive in the transaction log. So whenever you create a delta table, a fold structure are created. I'm just gonna go through in the slides, and then I'm just gonna give you a demo so you can visualize. So there is a delta log folder where all the commits of the delta table are saved in JSON files. And it's very important to understand that those files there, the JSON files of the log commits, is the source of the truth. So when you are using an engine, whatever engine it is, most likely it's going to be a Spark engine to read those tables. The first place that's going to go to see the latest state of the table and the versions of the table is going to be on the delta log folder. Even though there are the underlying data that are saved in Parquet files, so these are the data files that is on the root directory of the table folder. And then you can have as an optional the data files organized in subfolders that are called partitions. It's a way to kind of like index the table and make it easy to read the data and more efficiently with better performance. But with the advent of liquid clustering, I think partition is something that's gonna be with time phased out, because there is very little use case or conditions that would be logical to use partitions, because now you have liquid clustering, which is more efficient. But it's not the topic of this video. The other thing that I would like to explain is the checkpoint files. So the checkpoint files are Parquet files that sits in the log folder, and then I'll explain why they are created. And also I'd like to go through on how isolation atomicity works with an example, which involves also concurrency. So let's go for the examples in the slides here, and then I'll give you an example with a notebook. So as I said, this is the structure of the delta table. Usually there is a folder, not necessarily the name of the table. It can be a hash if you are using a meta store, but that's pointing to where the files of the table is. So first you have, whenever you create a table, the first thing that it creates is a delta log, and the first commit is this 00000.json file. From there onwards, it's added like an additional number for the subsequent commits. And then on the root directory, you can have Parquet files, which are the data files, which is where the underlying data of the table resides. And optionally, if you done partition on your tables, those Parquet files for data files are saved inside these partition subdirectories. So, as I said, this JSON files is where it says the version of the table and which data files that version points to. So that's why whenever you read a table, you first look at the commit and what commit you want to read, and then that JSON file is gonna say, okay, for this version, go and get this Parquet file, and then the table is loaded. So one of the reasons that, and then you can do time travel in the table, like you can read the table of different versions, and then I'm going to demonstrate that into the demo. So one important aspect of the transactional log is that at certain number of commits, a checkpoint file, Parquet in the log file is created, which is basically a snapshot of the table at that version. So the reason for that is that because with the history of the table, a lots of commits happen, and then it gets to a point that you can do a snapshot. And then let's say if I wanted to read version 12, you don't need to read from commit 0 to 12 to know the state of the table. You just go straight into the version 10 plus 11 plus 12, you got to 12, which I'm going to demonstrate in this slide here. So because the delta logs is the source of the truth, let's say I first reading the table in a Spark session, and then by the time I do the first read, the table is on the version 7, and that is the version that's going to be cached for my first read. And then let's say that within a few minutes, other users or something happens, multiple commits happen in that time. And then when I have to read that table again, it finds out the last version of the table is version 12. So it don't need to go back to see all the changes 8, 9, 10 from 7. It straight goes to 10, see the snapshot of the version 10, and they just add 11 and 12 in a way that makes it much more efficient, and that new version is then cached. All right, so I'm gonna talk about of what architectural decisions were made in terms of concurrency. Let's say two users are trying to make changes on the table. So in this case, one user are going to win first. So the way it happens is go one transaction at a time. First, let's say user one commit the transaction if there is no conflict from version 0. Usually is an append situation that's going to be very easy to approve. So what's going to happen is version 1 appends, and then version 2 is kind of like silently fail, but and then doesn't give a message for fail, and then it tries again, but on the second try it reads the latest version which was successful, which is version 1, and then that's committed. If there is no conflict, that commit is gonna be fine. But if on a retry there is some commit or there is some operation like delete or update and there's some conflict, and then that transaction fails. And that's called like solving conflicts optimistically. So that was a decision because they wanted the Delta Lake to be very efficient. In a scenario of data engineer, the most likely operation is going to be append. All right, so this is an example of how to do time travel using SQL and use Python. I'm going to demonstrate that in a notebook, and then you'll see it how it's done. And then I'm just gonna paste this notebook in my GitHub so you can do it yourself. So before going to the example, I'm just gonna talk about a little bit about vacuum, which is vacuum. It depends on how you want to retain your logs. So the vacuum actually doesn't clean your logs. It cleans or deletes the files that are not no more referenced in your logs. So there is no logs history that's reference files. So there, Databricks say, or the creators of Delta, whoever, whatever platform you are using, does not recommend to keep log indefinitely. So because that's gonna cost lots of storage, because the logs have every single change in your table. So logs are more for backup or oops scenarios. Let's say you delete a table, or you delete some rows that you shouldn't delete in a update or whatever operation you wanted to do. And then you can easily roll back or restore the table. The recommendation is that to be less than 30 days to keep the logs, and the files about a week. I think it's safe. Some people uh, set up those both to 30, but over 30 it's gonna be too costly for storage. So the defaults are 30 days for the logs, 7 days for the files. So a more efficient way to store history, you can use SCD type 2 or slow change dimension type 2, or you can use snapshot backups. Let's say I have a snapshot of this table. It can be monthly, it can be daily, it can be hourly. It depends on the type of table that you are looking at. Or you can do ST type 2, it's going to have all the changes only for the rows that change in that table. So when you vacuum a table, it's going to look at your table properties, and there are two table properties. There is the table properties for the retention of the files, and there is the table property for retention of the logs. So for the retention of the logs is log retention duration, and then the files obviously is deleted file retention duration. All right, and these are the defaults: 30 days and 1 week, which is 7 days. You can see on this documentation here more details about it, which I'm gonna go through. All right, so let's go to the demo. I have a Fabric notebook here. I'm gonna to run one by one. So first I'm gonna upgrade pip just in case. Fabric is very good because it has got some pools that you can start a new cluster in 5 seconds. So you can see in 5 seconds, and then it really is very efficient. You don't need to wait like 5 minutes. It's like serverless in Databricks, but as a default. All right, let me run this, and I have some program here that I created, like just to create some records in a table that I called sales. It doesn't matter what it is. I'm just would like to focus on the logs here. All right, let's create a table. I'm just gonna create a simple table here called sales. So by the, and then the first thing, as this one finished. Yeah, let's create a table. So, oh, the table was already created. I'm just now inserting some files. So let's refresh. Table is created. If I go on the lake house here and go on my tables, Let me refresh. And then I go here in view files. You see that there is partitions like data file, not in partitions, data files that was created for every commit. And if I go my Delta log, I've got these JSON files here, which are my commit files. And then I can get in it just to show you something. This first one I think was when I just created a table and set up like a schema for the table. And then subsequently I start to add some data, and then some data were created here in the table. And it's everything recorded here. So you can see the table with the data. We're loading a preview here. Right. So one interesting thing here is that I can see the history of the table. Yeah, you see like I have 11 versions, 0, and then I did like 11 inserts of data. And then with that, I can do time travel. There is an integration with the Spark Read API. I just need to pass the format delta and options version as off. Let's see version 1 and 2. And let's save those into data frames. And then I'm just going to run this to see how many records I had in each version. So you can see that first version I inserted like for every loop I inserted 20 records, so you can see 20 and then 40. But you also can query timestamp. So let's see the timestamp for the, let's say, version number 6. Just gonna copy this one. Timestamp's a little bit hit and miss. So if you give the exact timestamp, it's gonna give the exact version for that timestamp. However, 6 times 20 is 120, so that's version 6. So you can kind of like give different milliseconds here. Let's say 27 seconds and 00 milliseconds to see if you can fetch a version. Yeah, it's giving me an error. So let's see 727. 727 38. Is it gonna give me a version? It's a little bit out of a hit. I mean, sometimes you don't give an exact one. Let's see 38. So 727 38. Let's see if that works. Yeah, this one works. Probably, let's see which version it's gonna get. Yeah, it got the version 6. So you can do like not exact. It's gonna be probably, I don't know the rule here, but it's gonna get something like that's around that. I don't know if it go round up or round down. Anyway, so now let's look at the details here of the table. That's gonna show me lots of metadata of this table, like the location, description, catalog, etc., format. But there is this column that says number of files. So at the moment I have 11 files. So, but I wanted to do a file compaction. I wanted to reduce that to one file. That's our best practices too. You can do that with something called Optimize. That kind of like you can set up log retention duration, and then once you do Optimize, it can reduce the number of the files. But you have the option to say which is called repartition. Repartition in the sense that you give the number of the files that you want to reduce the table. That's a best practice recommended by Delta. So if I run this and I wanted to get that sales table rewritten, no data change, to one file. Now if I run that, So what's gonna happen? It's gonna create that one file. Good. So, but if I go there on the folder, it's still like now I have got 12 files. It hasn't reduced yet. You see, like it created like an extra file. But if I run this thing again, interesting enough, it's gonna say that I have still one file. So if I do this thing, it's still gonna work. But what I'm gonna do now, I'm just gonna run a vacuum, and I'm just gonna say, don't look at the retention duration property of the table. Just like do whatever I pass into the vacuum command. So what I'm gonna do, like I'm just gonna get the sales data table and vacuum and say, I don't want to retain any files that's not right now. And look at what's gonna happen. If I go here and refresh, the files are all of the table is in one, but I don't know which is the information of the table on version 1 or 2. Maybe it is like compacted everything into one. But it created like new versions like from 11, 12, and 13. We can see in the history here. So operations like create replace when I repartition. And I did a vacuum here that clear all the files that was not referenced anymore. But guess what? Because I still have the logs here, I can still build those versions with no issues. There's no problem because the logs are still there. However, let's try to now change the delete file retentions and the log to 0, because this one I've already done before. So, and then I haven't written more data there. So this one is not going to change much. So if I run this one, it's gonna still show one file. And if I see my properties, you see that the properties were changed. Yeah, and then I do another vacuum and just say 0. I'm just gonna freeze this. Yeah. Then if I do a history again, and all my versions are still there, and then I still can, for now yet, check my versions. This is why the logs, whenever you do a vacuum, even though you put log retention to 0, it wipes out the data files, but it doesn't wipe out the logs. The logs are kind of like managed by Delta. So the documentation says that the checkpoint operation kind of like eventually clear the logs. So if you see the documentation, let's go on that page. And I just wanted to say a few things here, which is very important before I finish the video. Let's have a look. So what it says is important. Vacuum removes all files from directories not managed by Delta Lake, ignoring directories beginning with underscore. If you are storing additional metadata like structure, stream, checkpoint without the table directly, use directory name as, yeah, that's a good recommendation if you don't want your checkpoints to be deleted. But that's more important. Vacuum deletes only data files, not log files. Log files are deleted automatically and asynchronously after checkpoint operations. The default rotation period of log files is 30 days, configuration through the delta log retention duration. All right, so another thing is the ability to time travel back to a version older than the retention period is lost after returning back. We saw that if you still have the logs, but the data files are not there, it still works. The problem is that once the logs are deleted, it's over. All right, I think that's all I would like to say. So if you have any questions, put on the comment below. Thanks for watching, and if you haven't subscribed to the channel, please subscribe, give a like, click the bell, and see you next time.